Okay, so question number 2 is what is the Lewis structure of NH2CHCH2 add lone pairs and multiple bonds, and then draw the valence bond picture of the sigma bonding framework. Okay, so first we need to find the Lewis structure of this compound. And the first step in finding the Lewis structure is to calculate the total number of valence electrons. In the case of nitrogen, nitrogen has 5 valence electrons. Carbon has 4. And we have 2 carbon atoms here, so we multiply this by 2. And hydrogen has 1 valence electron. And there are 5 hydrogens, so we multiply this by 5. And then if we add this up, we get a total of 18 valence electrons. So now let's start off by writing the Lewis structure. So we kind of get a hint of what it might look like because of the way the equation is written down. We have a nitrogen with 2 hydrogens bonded to a carbon with 1 hydrogen bonded to another carbon that has 2 hydrogens. Okay, so notice that both of the carbons don't have a full octet yet, and the easiest way to solve this is just to add a double bond in between the 2 carbons. And if we count out all the electrons I've drawn so far, each bond contains 2 bonding electrons. And we have 8 bonds, so we only have 16 electrons drawn so far. So for the remaining 2, I'm just going to add them as lone pairs on my nitrogen. So this is the final Lewis structure of our compound. And the second part of the question is to draw the valence bond picture of the sigma bonding framework. Okay, so I was never good at drawing these, but it can be pretty simple because you just need to draw your atoms like so. Let me do the hydrogen in a different color. So we have 2 hydrogens, and we can show the sharing of electrons. Let me just draw this a bit more. Between the nitrogen and the 2 hydrogen atoms. Okay, so then we draw a bond like this. And we can also show hydrogens. Just to show the sharing of electrons. And nitrogen has an extra lone pair. I'm just going to draw that over here. Like that. And notice that the bonds that are formed between nitrogen and hydrogen are sigma bonds. And we can see that it has head-on overlap. Overlap. Okay, so now let's try to do the same thing with our carbon. So I'll draw the 2 electrons shown in the middle that are being shared. And you can see another sigma bond is formed between the carbon and the nitrogen. And I can also show my hydrogen up here. And there's another sigma bond between the carbon and the hydrogen. And we have another carbon beside it. So let's do it in this purple color. And notice that there is a double bond. So when we have the formation of a double bond, there is still a sigma bond that connects the two carbons. So let me draw this in the same way we've been doing so. But now, both of these carbons have unhybridized p orbitals. I'm just going to show it as this long unhybridized p orbital like this. And this is shown on both of the carbons. And this is how the double bond is formed. So they're kind of connected like this. And we can label this bond as a pi bond. So this is when you have side by side overlap. Okay, and then just for the last carbon, it has two more hydrogens bonded to it as well. And then we just draw those two sigma bonds. Like so. So sorry if it's a bit messy, but this is the valence bond picture of the sigma bonding framework. So I'll just label this whole thing as the valence bond picture. Okay, so now let's see what the junior tutor said. Step 1 is to list the elements, their valence electrons. Just give me a second to count that out to make sure that we have a total of 18. Yeah. And determine the total valence electrons if the charge is present. Add the value of the charge to the total valence electrons when it is a negative. Subtract if it is positive. So they have 18 in total, and they got this skeletal structure of our compound, and they added the remaining electrons on our nitrogen because we have 18 valence electrons. Okay, so that's correct. And now the valence model is shown below. The sigma bonds are head-on overlap of orbitals and are represented by the overlapping shapes, while the pi bond, which is a side-to-side overlap of the p orbitals from both carbons, are presented by the dashed line. Okay, so they got the same structure. It's much more neat. So this solution is correct.